Okay. All right. Well, welcome guys. I'm going to be teaching this class through video. It's an empty classroom, so I decided to bring a couple of special guests. I have two bears, Buford, you'll see him a little bit later, and Genevieve. They're going to be sitting in, taking you guys' place as a substitute until we actually get students in here later on in the semester, or if Lord wills it to be in August. So I know this is a little bit strange. It's strange for me. I can hear echo. I don't know if this echo is going to appear in the video, but maybe I can figure out a way to get rid of that later. But let's just pray. Let's pray. Father God, we thank you, Lord, for this day. Thank you for the class, Father God, that is here in Laterno University, and the class that is far away all over the United States, Lord God. We pray, Father God, that you keep them safe, keep them whole, Father God. You reduce their fear, Father God. You reduce their angst, Lord God. And we just pray, Father God, that you, Lord God, will just be in the midst of every situation and in every circumstance, Lord God. That you will guide us, Father God, as you have always guided us, Father God, in every situation and every circumstance, Lord. We thank you, Father God, for your love for us. In Jesus' name, amen. All right, so I'm just going to get started. We'll start doing devos later if I don't look silly doing all this stuff that I'm doing. Let's start off with our topic, right? We're in chapter 3, 3.1 and 3.3, I believe is what it was, which is determinants. Remember I told you guys that I skipped ahead because there was row space and column space and stuff that we're going to look at later. I wanted to do something that was a little bit easier right before the break. And we talked a little bit about determinants on Friday, right? And we ended up with something called the cofactor method. So the topics for the day. Topics for today. And let me turn on this light here, make it a little bit brighter. Topics for the day. I'm going to do a couple more examples with the cofactor method. We've already looked at some before. Okay. 2, I'm going to talk a little bit about sparse and dense matrices. And 3, one of those things that all the engineers like, which is Cramer's rule. Okay. Well, those are what we're going to look at today. Now, just kind of give us an idea, right, of what we want to do. Let's remind ourselves about the cofactor method by doing a couple examples. And here I want to find the determinant. Using the cofactor method. Okay. And here I have this matrix, which I call A, right? Always a good name for a matrix. Here I have 1, 2, and 5 going across, 2, -5, and 4, 4, 0, and 1. That's what I have here. I want to find the determinant of this matrix. So we know how to do using the diagonal method, right? Which works for 3x3s like this one. So I could use the diagonal method to find the answer to this problem. But I want to use the cofactor method, right? And for the cofactor method, I can use any row or any column that I can expand upon, right, to do the cofactor method. And what is a good row or column? What would you think would be a good row or column here, right? And it's going to be the row or column that has the most zeros, right? Because then you don't have to really write out that particular cofactor. I'm going to write it out anyway, but in general, you don't have to write it out too much, right? So column 2 would be a good column to choose, or row 3. Right, so column 2 or row 3. Now, which one do you pick? I would say pause the video if you're already familiar with the cofactor method. Pause the video and pick whatever row you want. Find the determinant of this matrix, right? So give me a second to do that. Now we're back, okay? I'm assuming that you paused the video and you found the determinant of this matrix. I'm gonna use row 3. Row 3. All right. So I can say the determinant of this matrix A, right, using the cofactor method, is going to be, in this case, I'm going to have -1, right? Row 3, right, is what we're using. So this is going to be, element 4 is the third row, first column. Third row, first column. So we have 3 plus 1, right? Times the minor of this guy, minor 3, 1. Plus, oh, actually, this is wrong. You guys would have stopped me right there. Times 4, okay, which is my element there, times my minor. Plus, we go to the next one. I have -1. 0 is the third row, second column element. 3 plus 2. Times 0. Times the minor of 0. That's 0, 3, 2, right? Plus the last one is 1 is the third row, third column element. So it's the -1 to the 3 plus 3 times 1, my element there, times the minor at 1. Now, what are these minors, right? We need to talk about that. What are these minors? And remember, we said last time that the minors are what you have when you delete. So for instance, the minor 3, 1 will be the determinant when you delete the third row and the first column. And you just look at that sub matrix that you end up with, right? So let's go to the next step here. -1 to the 3 plus 1 is going to be positive, so I don't need to write it. So it'll be 4 times the determinant of 2, 5, -5, and 4. Plus, well, actually, I have to say minus, right? Because -1 to the 3 plus 2 is going to be -1. So I can say minus 0 times the minor of that. Notice that I really don't need to figure out what the minor is, because 0 times anything is going to be 0 as long as we're not dealing with infinity. But suppose that it wasn't 0, right? So I get rid of the third row and the second column. And what would be the submatrix? Be 1, 2, 5, 4. So I'm going to put 1, 2, 5, 4 there. Plus, -1 to the 3 plus 3 is positive 1, right? Times 1, okay? Times 1. So it's a minor 3, 3, right? So get rid of the third row and the third column. What we end up with is 1, 2, if I did this right, 2, -5. Now, the nice thing about when I have a class who's actually here, right, is that if I make any stupid mistakes, you guys will be able to catch that and be able to tell me if I screwed up. So I'm assuming I haven't screwed up. If I haven't screwed up, Lord willing, right, then we're going to get the answer that we need to get. So let's figure out what this is. So let's find the determinant of this 2 by 2. We know how to do that, right? So 2 times 4, that gives me 8, minus a -25. Right? I did that right. This is going to be -0, right? Because 0 times anything is 0, plus 1 times. Here we have -5 minus 4. Right? This becomes, right, if we work it out to the next one, we get 4 times 33, I think, minus 0, is that -9? 4 times 33. What in the world is 4 times 33? I don't remember what that is. I always have to do it over here. Let's do some math here, right? 132. Okay, if I did that correctly, 132. So that 132 minus 9. And what I end up with is 123. It'd be sucky if this answer is not correct and I have to do this video all over again. 123 is what I think it is. Okay? We'll work this out. A good professor would have checked to make sure that all of his answers were right first, and then take the video. But that's not who you have here. You have Dr. Wesley, so you have to deal with that. Let's go to the next one, right? So let's talk about a different problem. Another example. Here's my next example. I want to find the values of K so that A is singular. Now remember what singular means, right? Singular means it's like zero, meaning that zero does not have a inverse, like 1 divided by 0 doesn't exist, right? So singular means like 0, meaning that A has no inverse, right? And we know that if the determinant of A is equal to 0, then A is singular. Now what is A in this particular case? So let's put it down. I have A is equal to K, -2, 1, 0, negative K, -1, 1, 0, 1. K, -2, 1, 0, negative K, -1, 0, 1, 1, 0, 1. So at the bottom. Okay. And so hopefully you guys are able to see all of this. All right, I'll just move it up. Let me double check the camera real quick. This is my first time, bear with me. Okay, you're able to see that, all right? So I know you just got a big in your face of Dr. Wesley looking at you, right? And just staring, coming towards you. I apologize for that. Let's go back to this problem. I want to use the cofactor method again, right? What row or column would you use, right, to be able to determine the values of K that would make this work? You have several rows, right? I mean, row 2, right, would be good. Row 3 would be good. Column 1 would be good. Column 2 would be good, right? I'm going to actually use again row 3. Let's not use row 3. Let's use column. Let's use column 1. Let's use column. So I'm going to span along column 1 here. And what I'm going to do is I'm going to find the determinant, set it equal to 0, right? So let's do that. So our determinant, and I'm going to have K. I'm going to have -1. This is the first row, first column element, 1 plus 1, okay, times K, okay, times the minor of K. Let's see if we can do this now. Minor K, get rid of the first row, first column, we get negative K. -1, 0, and 1. Plus, this is going to be 0, so I'm not going to write it anymore like I did over there. Plus, I have this element 1 is the first column, third row, first column. So this would be -1 to the 3 plus 1. And if you wanted to, you could actually put that this is really supposed to be a minus, right? It's going to be positive minus positive if you look at that, right? So the first one's positive, the next one's going to be negative. The next one's going to be positive. It doesn't really matter in this case because it's 0 here. So then I have -1 to the 3 plus 1, right? This guy here, times 1, times the minor, right? So we'll get rid of the first column in the third row. So we get -2, 1, negative K, -1. All right? So far so good, I hope, right? And then let's just plug in here, goodness, this is positive, right? So this is K times, let's see if I do this right, negative K minus or plus a 0, right? Plus 0, okay. I think I did that right. Plus, this, because it's going to be positive, 1 times. Here I have, what's that, 2? This is plus K, I think is what we have here. And if we work that out, I think we get something that looks like this. Negative K squared plus K plus 2. Okay. I want to set this equal to 0. Set equal to 0. All right, that's what I want to do. We can bring our calculators to the fore here, but we really don't need our calculators here. That's not necessary. More than we need to do. Actually, I think I have enough space to put the final solution here. We need to conserve board space, right? So I have negative K squared plus K plus 2 equal to 0. So it's the same as K squared minus K minus 2 is equal to 0. Just multiply everything by negative 1. I could factor that, right? I think that factors into, what's that, K minus 2 and K plus 1. Okay, so the K is equal to 2 and negative 1 on my two answers. So if K equals 2 or if K equals negative 1, right, I get then my matrix A will be singular in that case, right? And you can check this out for yourself, right? If you plug in 2, right, then that means that these rows and columns are linearly independent, linearly dependent, right? Meaning that there is a linear combination of those rows or columns that would give me another row or a column in that matrix. Or if I plug in negative 1, the same thing would happen, okay? And I'll let you play around with that. We should go on to the next thing, right? Otherwise this video becomes extremely long. And our attention spans might not be as long as they were when we're actually in class looking at me versus watching a video and looking at me. Although you can pause it whenever you want to go eat lunch or something. Anyway, let's talk about sparse and dense matrices. Okay, let's go over the definition here. Definition. A sparse matrix is a matrix in which most of the elements are 0. Right? What do we mean by most? Definitely more than 50%, usually 60, 70% of your entries are 0, right? That's what most people classify as a sparse matrix. However, that's not always the case. Some people just say if it's a little bit above 50%, right, we have more zeros than we have the non-zero elements, then we're good to go. So it kind of comes down to context where you're looking at. But usually you'll know it when you see it, when you see a sparse matrix. Okay, sparse matrix. And then we have another definition. A dense matrix is a matrix in which, I know this is going to be crazy, most of the elements are non-zero. This is amazing, right? So essentially we have the opposite occur, right? We have more elements that are not 0 than we have that are 0, right? For instance, this here would be considered a dense matrix, right? We only have 2 zeros, everything else is non-zero, right? Dense matrices and sparse matrices really come up a lot when you have a huge matrix, like a 10 by 10 or 20 by 20 or 30 by 30, those types of things. You'll have a whole bunch of zeros, and this can happen in engineering classes. You probably have seen this before. If you had any engineering classes or any class with differential equations, you get a lot of matrices that have tons of zeros, right? And only a few non-zero terms, right? And then a dense matrix is the complete opposite of that. Let's look at an example of finding the determinant of a sparse matrix. Here it is. Find the determinant of, here I have A equal to 3, 0, 0, 1, 0. Oh my goodness, it's going to be a 5 by 5. I think I need more rows here. Next row is 0, 1, 0, 2, 1. The next row I have 0, 1, 2, 0, 3. Next row I have 2, 0, 0, 0, 1. And the last row I have is 1, 0, 0, 0, 4. So 5 by 5, so it's 25 entries overall. Let's see. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 zeros, right? So this is 13 out of 25. So have a little bit more, a little bit more zeros than we have non-zero terms, right? So you can say, you can kind of hedge and say this is really not a sparse matrix, but there is a lot of zeros here. I mean, there's a lot of zeros. So well, we'll just say this is kind of sparse, right? I can add more zeros next time if you guys like. Note that this is a 5 by 5, right? So this is a little bit bigger, right? Now we have to figure out what row or column, right? What row or column would we like to use the cofactor method on, right? We have many options here. I'll tell you what that is a bad option. Row 3 will be a bad option, right? Because I have 1, 2, 3 elements that are non-zero, right? And a lot of these I have that are that way. But I can see at least one of them where I just have more zeros than I have non-zero terms, right? And that's column number 3, right here. You guys see it right here. Column number 3, this one right here, has more zeros than any other column. At least that's what I think, right? So column 3 seems pretty good. Let me give you guys a chance to see if you can work this out at home. So pause the video, right? Give yourself a chance to do this. I'll wait for you. All right, well, I waited for you. I hope you paused the video. You've done that. Let's work this out together. See if we get the same answer. I chose column number 3. See if we can get that together, right? Okay. So I have my determinant of A. Okay. Here, I really don't have to write all of these other zero terms. I can just look at the second, my only entry in column 2 that's non-zero. So I have negative 1 to the, now where is 2 located? It's the third row, right? And the third column. So this is 3 plus 3 times 2 times the minor. When we get rid of the third row and the third column, which leaves me with a 4 by 4, by the way. So if I get rid of the third row and the third column, right, what am I left with? If I do this right, I get 3, 0, okay, 1, 0, 0, 1, 2, 1, okay, 2, 0, if I did that right, yes, 0, 1, okay, 1, 0, 0, 4. Okay, so this is what I have now. Question is, what should I do now? What's the next step? Well, I need to expand again, right? I have to expand this new determinant, right? It's a 4 by 4, I need to expand again. What would be a good column or row to expand on? Again, I think the best one would be column number 2, right? So I'm going to expand on column 2. Right, this column right here has only one term. So let's do that. -1 to the 3 plus 3 is positive, so I don't really need to write. So I have 2 times. Now let's expand this one out, right? 2 times. What do I have here? I'm going to have -1 to the, this is going to be the second row and the second column. So this is 2 plus 2 times 1, right? Times, again, my determinant, I'm going to get rid of the second row and the second column in this case, right? So if I do that, I get 3, 1, 0. Okay, 2, 0, 1. I think I did that right, yeah. 1, what's the next one? 0, 4. I think that's right. Okay. So far, so good, I think. Okay. What's a good row column to use? Here I'm going to expand on column 2, right? Can you see it? Expand on column 2 again. Squeak, squeak, squeak. So when I come to my next step, I have 2. This is going to be positive again, so I really don't have to write it. So I have 1 times. Actually, I don't even have to write the 1, but I'm doing that just so you see those entries that we use. And then I'm going to expand along column 2, so I have -1 to, this is going to be the first row, second column. Okay, so this is going to be negative now. I'm going to delete times 1, and I'm going to delete the first row, second column, right? So what am I left with when I do that? I get 2, 1, 1, and 4 here. 2, 1, 1, and 4 there. Let's multiply this out, so I have 2 times 1. This becomes -1 times -1 times 1 times, this becomes 8 minus 1, right? Just showing you all the steps there, right? That's 7, I think. 8 minus 1 is 7. So I have essentially -2 times 7. That gives me a -14. So that was a little bit more crazy than the one that we just got to do with. We just did 3 by 3. We did a 4 by 4 on Friday before spring break. I guess I should really edit that out just in case I have to use these videos another time, right? But we did this before, a 4 by 4. Now this is a 5 by 5. I told my class before the break that I was going to scare the people who didn't show up on Friday before spring break with a 5 by 5. But here it is, the 5 by 5 that I was going to scare the class with. So hopefully you're sufficiently scared. If not, well, oh well. I guess there's enough fear in the world already. The last topic for the day, and we'll stop here, and I'll check to see if the video quality is of any worth at all and how well I did, is we're going to talk about Cramer's rule. This is a kind of a huge topic in engineering, right? Engineers always like to use Cramer's rule. So let's put it down here. Cramer's rule. Okay. And Cramer's rule says this: if a system of n linear equations and n variables has a coefficient matrix A with non-zero determinant. Means that it's non-singular. Okay. It's invertible. Then the solution x1, x2 to xn of the system is given by. I know this is quite a long definition here, but just bear with it, all right? It's given by, here we have x1 equals the determinant of a sub 1 over the determinant of a. x2 is equal to the determinant of a sub 2 over the determinant of a. All the way to xn, which is equal to the determinant of a sub n, all divided by the determinant a. You're like, what in the world are these a sub 1, a sub 2, a sub 3? What are these a sub n terms? What does that mean? And what it means is this, where the matrix a sub I is obtained by replacing the ith column of A. Okay? With the column of constants B in the system of equations. Okay. So if a system of n linear equations and n variables has a coefficient matrix with non-zero determinant, right? Non-zero determinant, then the solution x of 1, x of 2, x of n, my n tuple of the system is given by x of 1 is equal to the determinant of a sub 1 over the determinant a, x of 2 is equal to the determinant of a sub 2 over the determinant a, x of 3 will be determinant of a sub 3 over the determinant a, all the way until we get to our last column, which is the determinant of x a sub n divided by the determinant of a, where the matrix a sub I is obtained by replacing the ith column of a with the column of the constants b in the system of equation. So we need to talk about what all of that means. A lot to take in. A lot of you guys have probably seen Cramer's rule. It's not my favorite subject, and not my favorite way of solving a system of equations, but it's taught a lot. So we should talk about it. Let's start with an easy one. Here we go. Use Cramer's rule to solve. And here I have the system 2x1 minus x2 is equal to negative 10. 3x1 plus 2x2 is equal to negative 1. So use Cramer's rule to solve the system equation. Now, we know multiple ways of solving this system equation, right? We have Gauss-Jordan elimination, we have inverse matrices, right? And now we're going to look at one more way of solving this system. So let's look at it, right? First thing I want to do is I'm going to convert this to a matrix equation. All right, my guys, Genevieve, Buford, are you with me? All right. Those are the bears, if you've forgotten already, right? They're staring very attentively at the board, really enjoying the class. Okay. My matrix equation looks like this. I have 2, -1, 3, and 2. I have here x1, x2 equal to -10 and -1. Okay. Here's my matrix A, my coefficient matrix. Here's X, what we're trying to solve for. Here's B. I want you guys to notice what is the determinant of A. Let's find out what the determinant A. Remember, because Cramer's rule said that my coefficient matrix has to have a non-zero determinant. So let's find out the determinant of A. The determinant of A in this case, very simple, is going to be what's that? 4 minus a -3, right? Which is a +7. So non-zero determinant. This is important because we cannot divide by 0, right? And remember, for Cramer's rule, we'll be dividing by 0 over and over and over again. Okay. Now that we found out the determinant of A, let's find out the determinant of A1. So let's figure out what in the world would A1 be in this case. Let's put it here. A1. Let's look at that matrix. A1 would be the matrix built from A, where we replace the first column of A is going to be replaced by this column of B, -10, -1. So I'm going to replace 2, 3 with -10, -1. Let's find the determinant of that. Now the determinant of this, I think, is going to be -20 minus 1, which is -21. Okay. That's the determinant of A1. Now let's find the determinant. Let's find A2 and then its determinant. So A2, again, it's going to be built off of A, right? This matrix right here. But instead of replacing the first row, we replace the first column, we replace the second column. So we replace the second column of A with B in this case. So we get 2, 3, -10, -1. Okay. If I did that correctly, I get -2 minus a -30, right? Which is, I think, is a +28. +28. And let me dot these guys. Okay, that's the answers here. Okay. Now Cramer's rule says this. Cramer's rule says this. Okay. So my solution, I have the x1 is going to be equal to determinant of A1 over determinant A, which is going to be, in this case, -21 divided by 7, which is -3. And x2, right, x2, okay, guys, is going to be the determinant of A2 over the determinant A, which is 28 over 7, which is going to be 4. So that's going to be my answer. -3 and -4 are going to be my answers to this problem. And if you were to plug -3 and 4 into this system, right, we'll see that this is indeed the answer to this problem. So Cramer's rule is kind of a neat concept, right? How it works, fairly, a little bit convoluted. I actually like inverses and Gauss-Jordan elimination much better than this, but to each their own. Let's do one more. Now that we have an idea of how Cramer's rule work. This is the last problem for the day. I'm going to have to erase this, so hopefully you still have this in your mind. Here's the last problem. Use Cramer's rule to solve. Here's my matrix. I just put it into matrix form for you guys instead of having a system. I have 1, 1, -2. 1, -2, 1. 1, -1, -1. x1, x2, x3, okay, equal to 1, 3, -1. See if we can solve this, right? Give you a chance to work it out on your own. Multiple ways of doing it, right? Here we could use our calculator to find a determinant. Let me determine by hand. Just to kind of give us some more practice. I'll use the diagonal method for those who haven't seen the diagonal method yet to find the determinant of each one of these guys. Okay. If I can remember how to do it, it's going to be interesting to see. Okay. So here again, here's my A, here's X, what I'm trying to solve for, here's B. How many determinants do I need to find? I need to find 4 determinants. That feels painful. I don't even like it right now. I'm like, why did I pick this problem? Well, I should have chosen something different. Something with more zeros, much more zeros. Anyway, let's find a determinant of A. One, -2, -1, -2, 1, and -1. Okay. I'm going to use determinant symbols. Okay. Let me see, make sure I wrote that down correctly. Okay. Now for the diagonal method, right? We're going to use the diagonal method. I need to create 2 more columns, right? Stick it right next to them, which are going to be the repeats of these 2 columns I have here. So I have 1, 1, 1, 1, -2, -1. And I'm going to create some diagonals, starting at the main diagonal. 1, 2, 3. So my determinant of A is going to multiply along the main diagonal. I have 2 plus 1, and this is going to be, I think, plus 2 again, when we multiply these numbers together, minus, I'll multiply, starting from the off diagonal, I'll do the same thing and subtract. Okay, this is going to be 4, I believe that's right. This is going to be a -1. This is going to be A -1. When you work this out, you get 5. Oh goodness, what's that? -2, I think. 5 minus 2, which is 3. Again, I wish you guys were here to make sure that I'm doing this right. But 3 is what I have. 3, okay? That's my determinant of A. So we'll keep that in our mind. And now I need to do the same thing again, but I have to do it for 3 more of these guys. This is painful. Oh my goodness. Let me erase this. I have to make sure I conserve my space, right? Usually I can just continue writing to the right or to the left, but I need to make sure that the board is in the camera view. Hopefully there's enough battery power to last to the end of this last example here. Let's look at A1 real quick. So I'm going to find the determinant of A1. So let's try to do this all in one step, right? I'm going to replace the first column of A with 1, 3, -1. I'm going to find this determinant. determinant of this guy, right? I could use the cofactor method, but I'm going to use the diagonal method, right? So I would need to replace, I need to repeat the first two columns again to the right. Create diagonals. Okay, multiply this, right? I think that's still 2 plus or minus 1. Because it's going to be minus 1. And this is going to be, I think, a plus 6. Did I do that correctly? Minus, or the opposite direction, off diagonal. I think, if I did this correctly, this is going to be a minus 4 on this side. Okay. This is going to be a minus 1. Okay. And this is going to be a minus 3. Oh, lots of minuses this time. Let's work it out and see what we get. If I work this out, I have, what's that, 4? Nope, sorry. This is going to be 7 minus. Now, inside here, we have, what is that going to be, negative 8. So that becomes negative 8, which gives me positive 15. Okay, positive 15. Determinant of A2, I hope I have enough space here. Okay. Instead of replacing in the first column with B, I'll replace the second column with B of A. So I have 1, 1, 1. That's now replace the second column, 1, 3, negative 1, negative 2, 1, negative 1. Repeat the two columns I have there. 1, 1, 1, 1, 3, negative 1. Create my diagonals. Hopefully you guys are keeping track with me. You're still with me. Multiply this out, right? Let me put it on the side so I can squeeze one more determinant down here. So I'm going to put it on the side this time. So I have here, this is going to be negative 3. Okay. This is going to be plus 1. This is going to be plus 2, I believe. Minus. In parentheses. Let's go the other way. Here I have minus 6. I think. Minus 1. Okay, that's 1, I think. And another minus 1. Okay. See if I can squeeze it down here. That is going to be, oh goodness, negative 2 plus 2, is that 0? Minus, what do I have here? Negative 8. That looks weird. I hope I did this right. So I get 8, positive 8. I'm going to do this. Positive 8. If I didn't screw up, then make a mistake. Looking at it, trying to be sure I didn't screw up. But I don't see anything. I don't see any issue here. Just double checking real quick. I don't remember what the answer is, to tell you the truth. So let's suppose that's right, if I didn't screw up. If I did screw up, then I'll write an addendum of where I screwed up. Because it's going to drive some of you guys crazy if I did. And then the last one, the determinant of A3, we'll plug in wherever for the third column, I'm going to replace the third column with 1, 3, negative 1 in A. So I have 1, 1, 1, 1, negative 2, and negative 1, right? And then the last one is going to be 1, 3, and negative 1. Okay. repeat this first two columns. So I have 1, 1, 1, 1, -2, -1. Here's what I did before. Same old soup, just heated over, as my dad liked to say. Multiply this together, I get positive 2, I believe. 3. -1. Minus. Minus, minus, minus. Going the other way. Trying to be careful. Without you guys in the class, it's hard to get the energy that I'm going to get when I do this type of thing, but I'm going to try to do it for you guys as best I can. Let's see. I think that's -2. -3. -1. Okay. Let's add that together, so that's going to be 5 minus 1, that's 4, minus, okay, we look at the next one, okay, that's going to be, what's that, -5, -1, so -6. Okay. So 4 plus 6 is 10. Interesting enough. I thought these were going to all be nice numbers. That's why I'm wondering if I made a mistake. You guys double check. Use the inverse of this matrix, right? Solve this using the inverse and see if you get the same thing I'm going to get. So our final answer, if we did everything correctly, right? I'm going to put it right here. If we did everything correctly, my solution so the x1 is equal to the determinant of a1 divided by the determinant of a, which is going to be 15 divided by 3, I believe. 15 divided by 3 is 5. x2, determinant of a2 divided by determinant of a. I get 8 divided by 3. And x3, we have the determinant of a3. Divided by determinant of a, and I have 10 over 3. This is the solution I have. I guess I really don't need the boxes since it's already boxed essentially in this corner. Right? So that's Cramer's rule, right? As long as I didn't make any stupid mistakes, right? I'll double check after this video and make sure that I didn't screw up anywhere. But I think this is probably right. It's probably right. Probably. So that's it for today. Thank you guys for watching, if you did watch the video. And I hope you guys are being safe. Take care of yourselves. Love you guys. I hope to see you guys soon.